We are going over gravity today. So Newton's law of universal gravitation force tells us that as long as you have two objects and they have mass, as long as they have masses, there would be an attractive gravitational force between them, and it should be calculated as gravitational force equals G times mass of object 1, mass of object 2 over the distance between them. And G is a universal constant, 6.67 times 10 to the negative 11. Now, notice this is a very, very small number, and G has to be determined experimentally. So let's try to have a look at our ordinary everyday life objects. What would be the gravitational force between our everyday objects? So let's say we have object 1.5 kilo, object 2 also 0.5 kilo. The distance between them is half meter. What will be the gravitational force between them? So you just plug in all the numbers. So G, gravitational constant, capital G, mass of object 1, mass of object 2, distance between them. You find that the force is 10 to the negative 11 Newton, which is very, very small, and we cannot sense it in our everyday life. But in our everyday life, we can sense the force from the Earth, right? The gravitational force, which is our weight. Now, first example, what would be the acceleration due to gravity on the surface of Earth? So from Newton's law of universal gravity, the force that acting on any object on surface of Earth, G, mass of Earth, mass of the object over r squared. R is the distance from the object to the center of the Earth. So this is R. Now we also know weight is m times g, and g is acceleration due to gravity. So if you compare equation 1 and equation 2, we have g, the lowercase g, acceleration due to gravity is capital G, mass of Earth, over r squared. R is the distance from the object to the center of Earth. So if the object is on the surface of the Earth, then the distance is r, which is the radius of Earth, and we know radius of Earth is 6.38 times 10 to the 6 meter, and the mass of Earth is roughly 6 times 10 to the 24 kilogram. So if you plug in all the number, G is 6.67 10 to the negative 11, and the mass of the Earth 5.98 10 to the 24, distance, which is the radius of the Earth, square, meter per second square. And you put this into your calculator, you should find a number very close to 9.8, and that's why we use 9.8 for free fall. Now we have studied that the centripetal acceleration, if you remember, the centripetal acceleration of the Earth orbiting around the Sun is roughly 6 times negative 3 meter per second squared. That's what the example we went over in the lecture, uniform circular motion. So which means the centripetal force on Earth should be mass of Earth times the centripetal acceleration of the Earth. So you should at least have a force like this, 3.6 10 to the 22 Newton on Earth, so the Earth can orbit in its orbit. If there is no such force, then from Newton's first law, the Earth will go with constant velocity. But fortunately, we have a force from the sun's pull on Earth, the Earth is keeping on its orbit. So let's calculate what's the gravitational force between the Earth and the Sun. So you need to use this universal law of gravity. You need to use mass of Sun, mass of Earth, distance between the Sun and Earth. To plug in all the numbers, you should get 3.54 times 22 Newton. So you say Fg actually indeed roughly equals to the Fc. So Fg is the source of the centripetal force on Earth. That is majority of the force. Of course, because you see there are other planets surrounding Earth. So those planets might also have a gravitational force acting on Earth, and that's why Fg is not exactly like Fc, but very, very close. Now let's discuss satellite. So when a satellite is orbiting Earth, what's the force keeping the satellite in its orbit? Of course, it's a gravitational force from the Earth. The gravitational force on satellite should be calculated like this. G, capital G, mass of the satellite, mass of Earth over the distance from the satellite to the center of the Earth. And the gravitational force should equal to the centripetal force of the satellite doing uniform circular motion. Now the centripetal force of uniform circular motion is mv squared over r. So that's basically our starting point for all the problems we have in this chapter. So you have a simple relation if you want to send your satellite into orbit with radius r to the center of Earth, v is fixed because g is constant, me, which is mass of Earth, is constant. So there is a one-to-one correspondence between the orbit and the velocity of the satellite. So let's check a very special case of satellite, the GPS satellite. So for GPS satellite, it's relatively fixed to the ground. So when Earth being one day, the Earth spin one circle, the satellite also spin one circle. Now we know one day is 24 hours, which means the satellite move one complete circle in one day. So which means the period of the GPS satellite should be 24 hours, one day. And if we translate 24 hours into SI unit second, one day we have 86,400 seconds. Now we want to know what will be the distance, how high you need to send this satellite to outer space so it can be a GPS satellite. So we start from the equation, the gravitational force on satellite. That's gravitational force on satellite equals to its centripetal force. In this problem, they are not interested in velocity, they are interested in period. Sorry, this is not t. So interested in period, but there is a relation between v and period. So v is 2 pi r over t, we haven't learned. So we replace v by 2 pi r over t squared over r. So it's m 4 pi r, 4 pi square r t squared. So you can solve for the orbit from the above equation. You find r cubed should equal to g, mass of Earth, period of the satellite, over 4 pi squared. So r is square root power of 3 gm e t squared over 4 pi squared. So you plug in all the numbers, you find is roughly 4.2 times 10 to the 7 meter.